just a brief confirmation from your side. You can hear me and see my screen, right?
Yes, it's
Oh,
perfect.
thanks. So we'll wait another 1 2 minutes for other participants to join, and then we'll start. Okay, I guess we can start now. So welcome you all to the fourth problem solving session for this class titled 5G Wireless Standard Design. So let me introduce a new slide here. So this week content is mostly about receiver design, right? That's primary difference compared to previous 3 weeks content. So when you talk about receiver side processing, what is the first block we should consider? Like what happens? We are not talking about the RF processing, just the in baseband processing. What is the first step we need to do when I receive something over the air at the receiver side?
You mean when we receive the IQ block?
Yes.
Then first we should go for CP removal.
Okay. Fine. But the issue is what we are receiving analog signal, right?
Yes. So
So
we will require ADC analog to digital converter,
okay, okay, fine.
both for I and Q separately.
So at receiver side, if we talk about receiver side, whatever is coming, you were saying we should feed it to ADC. Good enough. And then
Then we have to combine it and then we will go for CP removal.
fine, we remove the CP. And what is our next task?
F- FFT.
And why we need FFT here? Because we need to, yeah, you are saying something.
to obtain frequency analysis.
Okay, yeah, correct. So basically we need to bring whatever we have received in frequency domain. As of now they are still in what domain? Like before FFT.
So time domain to frequency domain conversion.
Yeah, so we are time domain still now. Whatever we receive this time domain analog signal. So first we pass it through ADC, both real and imaginary components. So that makes it a time domain digital signal. Fine, CP removal happens, and then we have to go for FFT to bring those symbols samples in the frequency domain. So after FFT, what we obtain? Like we obtain some kind of grid or something. Like once I do FFT, what I am going to see?
The demodulated signal.
Demodulated signal. So let's say I am performing FFT over a certain interval. So what am I going to have? Something like this rectangular grid or something? Here you have time. Basically when I say time, it's basically the number of symbols, and in y axis what do we have? The PRBs, right?
Resource
Basically,
blocks.
yeah. So or if I want to break down for the subcarriers, so I'm going to receive some symbols here. Good enough. I have now time frequency grid. So I have my symbols. What next?
Then we have to demodulate it.
Demodulation will be required. Fine. So when we talk about demodulation, what exactly is it?
Obtaining message signal.
Obtaining message signal. But why you need demodulation in the first step? Why we cannot process the symbols directly from the time frequency grid here? We can take these symbols, right, whatever we have received, and can process it directly by bypassing the demodulation. Why not?
There are many processes like segmentation, uh, which should be decoded.
And okay, not exactly, I would say. So what I'm trying to emphasize here, what is the need for us, what is the need for demodulation here? We can directly process the symbols, right? So why specifically we need the remodulation thing, apart from the this thing that okay, transmitter side you have modulation, so receiver side you should have demodulation, something like that. Okay, that's the primary thing, but what else? What issues will be there if we don't demodulate and directly operate on symbols?
Because we have to extract the transmitted data
Yes,
out of FFT.
this is there. And so let's say somehow uh, that problem is not there. So what other issues will be coming? Let's say I want to directly operate on symbol basis, not these messages, that is zeros and ones. What will be the issue in that case? So I need LDPC decoder for each modulation scheme possible, right? Based on my SNR, whatever as a receiver I am feeding back to base station can transmit with starting from 4 QAM to 256 QAM in 5G framework, right? So if I plan to directly operate on symbols, I would need LDPC decoder for all these separate modulation schemes, and that's not really a viable option. So this is one reason I can think of. Second thing, what is the need for like demodulation in the first place, in the sense that let's say I am talking about QPSK thing. So if I would like to draw the constellation diagram, I have four possible things here. This is, let's say, 0 0, this is, let's say, 1 0, this is 0 1, this is 1 1. So in demodulation, what do you exactly do? We try to retrieve whatever is being transmitted, right? So how do you do that? So let's say I am transmitting this one here, 0 0, for any particular resource element. Am I supposed to get the receipt symbol also in exactly this position? What I am trying to say, at transmitter side for this particular uh, grid point here, I have transmitted 0 0. So at the receiver side, after performing effective, when I look at the symbol here, is it going to be the same in the constellation diagram? Like why, what should yeah,
We have to determine the most likely bits after the constellation mapping.
most likely bits, but why do we need that in the first place? Like why you need to go for that?
Because we are still on the physical layer.
Yes, true, but what I am trying to point out here, let's say you have transmitted 0 0 in the received at the receiver end. Are you going to receive exactly your receipt symbol at this position, or it can be somewhere here or here? Like usually what happens? That's what I'm asking.
It can be displaced.
Okay, often it is displaced. And what is the reason for displacement here?
Might be some errors.
Errors. And at what stage it's
And
introduced? Like what causes these issues? The symbols is mostly displaced, that's true, but why? That's what I'm asking.
time domain to conflict domain conversion might not be accurate.
Uh, let's say you have very high resolution FFT, so that
Okay.
situation won't appear. Let's say the blocks are also working kind of in ideal condition, so there is no issue from their end also. So what is the most fundamental issue that is going to cause this problem? That whatever you have at transmitter end, ideally it should be received exactly like at what condition it would be exactly the same at receiver end, when it will happen, when there is no noise, right?
Even if consider no noise, we are using different modulation schemes based on the signal levels.
Yes, true.
So the modulation schemes varies.
Modulation scheme varies, true. But that's one thing, like okay, for particular listener condition you are choosing this 4q psk thing, but when is that uh, whatever being transmitted will be received at the same position when there is no noise, right? Ideally, so noise is going to shift you. So if I see when the signal x is being transmitted and y is being received, so it's x plus n, right? So what is this n here?
Nice.
Noise. uh, at what end? Transmitter end or receiver end?
Transmitter.
And what is the source of that?
It is introduced in the channel.
um, okay, so yes, your awgn channel model additive white Gaussian noise is being added. So why we call it Gaussian, by the way? So this noise, this n thing is the fundamental reason this symbol is going to be shifted in the constellation point, whatever being transmitted here. Let's say this one is 0 is 0 is being transmitted, it can be received very well somewhere here or here. So that's the thing caused by noise, right? So fine, I'm just asking like why we assume the noise to be Gaussian usually. Any particular reason behind that?
I'm
It
confused.
is random, so it is distributed like that.
Yes, but random variable can have all other sorts of distribution, right? Not only Gaussian. It's true, it's random, of course. So it can have many other distribution. Why we should go for Gaussian thing? So there are actually lot of different kind of noise at the receiver end. Let's speak about the first, thermal noise. So it's caused by the movement of electron. Since electrons, they don't move at uh, ideal temperature of minus 273 degree centigrade, but that's not usually happen, right? We usually have some uh, non-zero temperature, so electrons keep on moving and these movements are independent and that leads to noise. So whatever we see as n here is actually summation of many different noise, n1, n2, n3. So those are all kind of sum up and we are calling it as n. So what happens when, like, let's say there are many random variables, they can have any sort of distribution, but when they are summing up, does they sum uh, converges towards any specific distribution? What I'm saying, like n is consist of, let's say, n1, n2, n3 up to some nm, where nm is large number. Now this individual n1, n2, n3 can have very different sort of distribution. I don't know about them, but actually when I'm summing up all of them, summing up a large number of random variable whose distribution I don't know, does this sum has some specific distribution, or they move towards a certain distribution?
I think it is Gaussian.
Yeah, so it's in mathematics we use central limit theorem. So central, the essence of central limit theorem is when you have a large number of random variable and you sum them up, so essentially the joint distribution becomes very close to being Gaussian. So that is what is happening here. So fine. So we already know that received signal in the constellation diagram is moved elsewhere. Fine. Now how do we retrieve that? Anything you can think of? Like for let's say 00 is ideally here, but now I am receiving it as this. So how do I know that 00 is being transmitted? What do we exactly do? At the receiver end I have to do something. I know that QPSK is being transmitted because I have only informed about that choice 2 base station. Now I know the constellation diagram of QPSK, and now I am seeing that my received signal is here, which I clearly know is not being transmitted because for QPSK only uh, legitimate constellation points are these 4, and what I am received is something here. So what should I do now?
Distance from the origin will give the error.
So
Respective distance.
I will compute the distance of which this one here.
Yes. Both. And take the difference. It will give the error.
So I have to take the distance of this point from all of them or only one?
Origin.
And what is the full form of that? Okay, as you said, we do something called nearest distance detection rule. So basically, as you told, we are going to compute this distance here, this distance here, this one here, and this one here. And then what we do?
Which is the nearest one, we will take it.
So if this one comes out to be closest to 00, I will assume that 00 is being transmitted, right?
Yeah, yeah. Yeah, correct.
And when I will be having error, just in this diagram, like for example I transmit 00, when is the situation when I will be in error, like at what point the received symbol should be to cause error in according to this rule? So let's say 00 is transmitted and I am assuming that this particular zone, out of this zone the received symbol appears. So do you think it's going to be in error or it can still be detected correctly?
It can be detected correctly.
Can it be detected correctly if we apply nearest distance detection rule?
Yeah.
So let's say the received symbol is here, so and I compute nearest distance detection rule, which one, which constellation point the receiver going to choose?
10.
10. So I originally transmitted 00, but the receiver had now make the decision 10. That is what we call hard decoding. So then it's we are in error, na?
Yes.
So we are talking about just nearest distance detection rule here, not about the other kind of error correction and detection. Just forget about them. This is just only we are talking about nearest distance detection. So whenever it's out of this region, you will have trouble, especially if you do hard decoding kind of thing, because you have transmitted 00 and you have make your decision as 10. Now this error will kind of get propagated. So that's okay. We'll see how that can be encountered. So demodulation is done, fine. What comes next after demodulation? Sorry, I cannot hear you. Can you repeat once?
Descrambling.
Descrambling. Correct. But I have one question here. Like, what does descrambling mean here? Like, just a one-liner, maybe. So you are saying I have some sort of sequence from demodulation. Let's say this is demodulation block. I have received some sort of binary sequence. So now you are saying descrambling. It should go into descrambling. So what does this block do?
Because after demodulation, the sequence might vary from the original transmitted sequence.
Yeah, that's okay. That error can be there. True. But does descrambling really worry about those errors?
No.
It's not his task, right? So what does it
Yeah.
basically do? So okay, let's go to the transmitter side. What was the task of scrambler? What its main purpose was? To remove error or do something else? If you
To
remember.
scramble the bits by using some sequence,
So
by
scramble
XORing
the
with
bit.
some sequence.
True. And what was the purpose of doing that?
Continuous bits should not be there.
So you are saying that average power constant should be maintained.
Yes.
That was the goal of scrambler.
Yes.
So to descramble is to like undo its effect, right? So for that, what it needs to do?
XOR with the same sequence, what we had used for scrambling.
Okay, I will XOR with the same pseudo random sequence. Fine. But my question is that at transmitter end you do scramble with some pseudo random sequence. That's okay. But to descramble, can we use some other pseudo random sequence or I need to use the same?
Same one.
Why is that?
We need to get what we had done in transmitter back now.
Okay, so only the same pseudo random sequence can undo its effect. That's what you are saying.
Yeah, correct.
Fine, but how user know about that? Because that is what something base station have done.
We have to get the correct coding also, whether it is polar or LDPC.
Um, can you repeat once? I didn't hear you properly.
And I'm saying we have to get the correct coding also, whether it is LDPC or polar. So what are the type of coding?
Yes, yes, like that part will come to later if you remember the
Okay.
transmit side, like LDBC encoding we have done, and then we have this red
Yes.
matcher and this all that. That part will come, but now,
Okay. LDPC decoding will be separate. You got
yeah,
it.
yeah, like whenever we are talking as of now, we are talking about LDBC decoding only, but we'll come to that later,
Mhm.
like working of that. But now let's just focus on the scrambling part. Like as of now we have reached the consensus that okay, we need to use the same pseudo random sequence exactly to undo the effect of scrambling that is being done in transmitter end. Fine, but how do user know that pseudo random sequence? Because that is something base station use at its end. Now we are saying we need to use the same pseudo random sequence. So how user get to know about that? So as of now we have mostly talked about physical downlink shared data channel, right? But there is another thing, physical downlink control channel also. So actually this information is feed to user. Base station only feeds, but base station doesn't transmit this information in the same channel it's transmitting the data. It is transmitted via PDCCH or physical downlink shared control channel. So there it will inform the user that I have used this pseudo random sequence and you are going to use that also. So when it comes to implementation of pseudo random sequence, I have this question. Let's last time we have seen, or we have seen in the lectures also, when scrambling is done on the concatenated code blocks, right? So we have seen the standard example where we have four code blocks, red match code blocks, each with 11340 bits. So uh, and you apply this concatenation thing, fine, concatenate, and so altogether you get a payload of 45360 bits, and you scramble on that. So perform scrambling, we need a pseudorandom sequence of 45360, right? So do we store this entire thing, because we need to use the pseudorandom sequence and that should be the same length as of payload. So how does it happen? Do we exactly need to store this 45360 bits, or we have some okay, first of all let us see in this way. Is it possible even to store this big sequence, or is it a viable option, and if yes, why, and if not also why? Whatever the issue, let's say I need a few pseudo random sequence of, let's say, 45,000 something, and I am going to save it. So what is the issue with that?
Implementation becomes difficult.
Yeah, because you will have huge memory overhead, and this is not also a single pseudo random sequence, right? For different user, for different task, you very well need to use different pseudo random sequence, and your payload size is constantly changing. So how you exactly mitigate this issue then? Any particular name that is used in 5G NR framework when it comes to the implementation of scrambling or descrambling? So for this purpose we use something called gold sequence, or to be more specific, length 31 gold sequence. And this sequence is kind of, oh okay, first of all we call it length 31. Why is that? Because it is generated from a 31 bit depth register. Register is nothing but a length 31 memory slot kind of thing where you can store these things. So can you tell me how this length 31 gold sequence is generated? So there are, when you talk about length 31 gold sequence, there are two different sequences. One is x1 n and another is x2 n. So whatever pseudo random sequence that we called as cn, that is obtained by XORing x1n and x2n. but this is only length 31, like it's limited. So we need to initialize those two sequence, and we need some kind of processing to continue generating them. So what is the procedure for that? Can you remember? Like every time you compute x1 and x2 and OR, it will be basically shifted towards right, so it needs to be fill in from the behind also, but there should be some principle so that you can generate the pseudo random sequence. So how it is basically done? So first we will talk about the initialization part. So x1n is usually initialized as this first bit here as 1 and rest of them being 0, and that's what we are talking about, the initial part. So first bit is 1, rest 30 bits are zeros. That is for x1. x2n is slightly different. So for x2n is based on a number user is being fed, okay, and that is called CRNTI. So its full form is Radio Network Temporary Identifier. So basically when a user entered a particular network, it is assigned a number based on its location, where that is, like that. So CRNTI is a number, that is what based on x2n is generated. So if I choose CRNTI to be, let's say, what should I choose? Let's choose 63. So my x2 sequence is going to be 1 for n varies from 0 to 5, and 0 for 6 to 30. So x1 is initialized kind of similarly, but x2n is based on the unique identifier of that particular user. So that is what the initial part is, and how these things continue. So basically you pick the x1 of 0 and x1 of 3. What you do, perform the XOR operation and feed it back. So this one is here is x1 of 3, this one here is x1 of 0. You are XORing it and feeding it into x1 of 31, and these things, like once you take the output here, the register shift rightwards, the entire bit sequence will shift rightwards, and you will have a new entry here. Similarly for x2n, the procedure is mostly similar, but just here it's x1 of 0 and x1 of 3. Here it's x1 of 3, 2, 0 and 1. All of them you perform XOR operation, and that is what it goes to x2 of 31 here. So new bit based on those previous values, this new bit is generated, it enters the register, and these two registers produce two sequences, and you keep on generating the pseudo random sequence using it. That's all. So let us talk about the next thing. Okay, before that let us solve a question. uh, so we are giving this kind of question, that for a given channel y is equal to x plus n, the PDF of noise is given as follows. Now you have to calculate the map threshold value alpha if the transmitter is transmitting BPSK such that 0 is mapped to -1 and 1 is mapped to +1. with some probabilities. So what do you think I should proceed? Okay, we have not, let me set the ground here. So the question is saying you are feeding some message here, message MIs, those are getting mapped to symbols. You do some modulation here, you are getting SIs, that is a symbol here. Here it's saying this is X, so let me change the notation. What I am receiving is XI, and then it passes through the channel, and noise is added. So at this end I have Y is equal to X plus N. So we have our received signal, which is the transmitted signal plus some noise, and we have to find something called a map threshold value. So let us try to understand few things. First of all, you have a message signal. It says that when message is 0, it's mapped to -1, that is when mi is 0, xi is -1, and when mi is 1, uh, um, xi is 1. It's passed through channel, noise is being added. Now you have a corrupted version of xi. This part will understand fine. So it's asked to calculate something called as map threshold value. So can you point out what map here is? What does map denote? This is received signal here. So we have seen already that nearest distance detection rule. So there we did not need much of a math. It's kind of more intuitive and easy to visualize. So when you talk about map threshold value, it's, you can see at certain scenarios it's only similar. There are certain differences, but that's okay. So map stands for maximum a posteriori probability. So what does it mean when I say map, maximum a posteriori probability? A posteriori mean you have already seen what your observation is. Okay, first of all I would like to ask, let us forget about all these things, let us talk about what is the issue here. Like can you just tell me what is the task here? Like we have Y, what is our task here? We have this scenario Y is equal to X plus N. So what we are trying to do here? Can one of you just point out that what is our purpose here?
Are you asking with respect to demodulation?
Yes, yes, because it is something happening at the demodulation block only.
To remove the noise and get the message signal.
Correct. So basically you are saying that you have Y, you know what your Y is. Now you want to know what X is being transmitted, right? That's what I was saying. So when I say map maximum a posteriori probability. So what does it mean intuitively? When I talk about a posteriori, it means basically we know why. Why here is our observation. So now we want to know the probability that X is transmitted. Can you talk about, can you tell me what are these things here that is given? P of X is equal to 0, 2 over 3, P of X is equal to 1, 1 over 3. What are these things?
This is the probability of for x equal to 0 and x equal to 1. This is the probability 2 by 3
Like
and
it
1
is,
by 3.
okay, so is it something to do with receiver side?
Yes.
Uh,
Because mapping is minus 1 to 1 and 1 to 1 with this probability.
no. Mapping is a kind of deterministic. Okay, let me mention that mapping is deterministic. I mean, when a transmitter ends, it's modulating. It's only a binary sequence like zeros and ones. So what it's doing? It is mapping 0 to -1, and it is mapping 1 to 1. That mapping is deterministic. There is no probability there. The probability, when it mentioned, it means that with what probability transmitter is generating zeros and ones. So when it says probability of x equal to 0 is 2 by 3, it means at transmitter side, when you observe over a large time interval, every 2 out of 3 bits are zeros and every 1 out of 3 bits is 1. So these are called message probabilities. Message probabilities. It is also known as priori probability or prior probabilities we can call. Why it's called prior? Because it has nothing to do with our observation y here. It doesn't really care about the observation. These are priori probabilities. It has nothing to do with receiver end. This is purely something, a property of transmitter side, that what transmitter is doing, with what probability it is transmitting 0 or what probability is transmitting 1. That has nothing to do with what we are going to observe. So that's why these are called priori probabilities or prior probabilities. And when we talk about a posteriori probability, that means that observation is done, like we have, the event has already happened or we have already known the y. Now we want to know what is the probability that x is transmitted. Now this is a good point to ask you, like let's say there is no observation. So what do you think, that what is the probability that 0 is transmitted if uh, I ask you that there is no concept of receiver, or you don't have knowledge of what you have received, the received signal is unknown to you, you don't know that. So what is the probability 0 is transmitted?
It is 2 by 3.
That is the same as the prior probabilities, right? Because you don't have any
Yes, yes.
observation, you
Yeah,
just know at,
correct.
yeah. But your probabilities now change when you have the knowledge of received signal. That's the issue. You have some prior knowledge that okay, with probability 2 over 3 0 is transmitted, or probability 1 over 3 1 is transmitted, that's okay. But once you have this received signal, then your probabilities can change, and that is what we call as maximum a posteriori probability. That is, the probability is conditioned on the knowledge of received signal. So that is what we are going to find here. So let me introduce a slide. So mathematically it is denoted as probability of, let's say, message signal. Let me denote x naught as -1 and x1 as 1. So this corresponds to 0 and this x1 corresponds to 1. So probability of x naught given y and probability of x1 given y, so these two are a posteriori probabilities. A posteriori probabilities. So there are different kind of receiver mean we talk about decoders. So let me point it out here, receiver here, or you can call it decoder. Please don't confuse with it LDBC decoding. When I talk about decoder, it is in context of demodulation. So receiver can be of different type. Let me talk about two of those. Let's say we talk about map here and ML here. Map we have already seen. ML is just maximum likelihood. We'll come to that. What does it mean? So when the question mentioned the map threshold, we should understand what does it mean by map receiver. So when I question is about map receiver, it means it is the receiver which maximizes the a posteriori probability and take decision based on it. So I give you this one line. Now I would ask you, what is the task of map receiver in the question given? So map receiver is the receiver. I told you that it maximizes the a posteriori probability and take the decision based on it. Now, and I also told you these are the two a posteriori probability for our case, because only it's a BPSK, either -1 or 1 is transmitted. So what do you think the principle of map receiver based on these three information? You have only two symbols to transmit, x0 and x1. At the receiver, it's map receiver. That means it maximizes the a posteriori probability and take decision based on it. And you have this two a posteriori probability corresponds to two symbol. Now based on this three information, what do you infer? What is the receiver going to decide? Or let's say, give me the answer when the receiver going to decide in favor of x naught. In favor of x naught. Like when the receiver is going to decide, when the map receiver is going to say, okay, x naught is transmitted.
Probability should be known for that. A posteriori probability.
Okay, let's assume we have the knowledge of a posteriori probability. Then when it's going to decide in favor of x naught?
When it is above certain threshold.
Who is above certain threshold, like which probabilities? There are two, p of x naught given y and p of x1 given y. There are only two possibilities, and the receiver has already seen the received signal, that is y. Now based on that received signal y, when it's going to decide in favor of x naught, let's assume we are given the a posteriori probabilities.
Which one is more, it will take that one.
Okay, so you are saying something of this sort: p of x naught given y is greater than p of x1 given y, right?
Yeah, correct.
So that means basically what you are doing, conditioned on the knowledge of the received signal, you are choosing the symbol whose a posteriori probability is higher. and it is going to decide in favor of x1 when p of x1 given y is greater than p of x naught given y. Now, are you familiar with the base rule? So p of x naught given y can be written in a certain form. What is that thing? Okay, let me start with little thing. Like, let's say this is p of x and y. This is the joint probability of x and y. So how it can be written?
Conditional probability formula.
True, true, correct. And what should I write then?
P of x not intersection of P of y divided by P of y, I think.
Okay, so when it comes to continuous random variables, it can be continuous and discrete, because here x is your, by the way, x is your discrete here, because there are only two possibilities, -1 and 1. Y can be continuous, of course, because it's a received signal. So as of now I'm going to use capital P for x because it's PMF, or for discrete probability. So you are saying something of this sort, right? P of uh, y given x, and this is small p, by the way. This is continuous. Is that what you are saying? That joint probability of x and y is written as p of x times p of y given x, right?
Yes, correct.
And what are the other expression possible? You have to just interchange actually x and y. So it's probability of y given probability of x given y, right? So what is this thing called p of x? We already just talked about it. What is the name for it? X is your signal here, sorry, x is your symbol here that is being transmitted. So what we call p of x?
Transmitter side probability.
It's prior probability, right?
Prior, yeah.
Prior, that has nothing to do with observation. It is a prior probability, purely transmitter side property. And what is this p of y given x? Like, let's forget about the maths part. What does it intuitively mean? P of y given x, that a given symbol x is transmitted, what is the probability of receiving y, right?
Yeah.
That's what it means, and that is actually called likelihood. That is actually called likelihood. So why likelihood? This actually denotes the likelihood of y given x is transmitted. So I'm talking about now map receiver in this question because it concerned with map, but there is a ML receiver possible. So what does ML receiver do? Basically, when we say ML receiver, that means receiver maximizes the likelihood probability and take decision based on that. But that's some slightly different topic altogether. We'll see that later. Now let's focus on these a posteriori probabilities here. So we have reached this consensus that it is going to decide in favor of x0, or it is going to decide that x0 is transmitted when the a posteriori probability of x0 is greater than that of x1. Fine. Now how do I compute that probability of x0 given y or x1 given y? So that has actually things to do from here. For example, you can see here px, you only already said that just a moment. Okay, p of x P of x times P of y given x is equal to P of y times P of x given y, right? So I'm going to use this formula only. So now can you tell me what is the a posteriori probability of x not given y? What it should be using this expression here? So you can see here this is a similarity between this term and this term. So basically what I need to do, I need to bring py in this side, so that will come below it, and then here I have probability of x naught and probability of y given x naught. Now this you already told that this is a posteriori probability, fine. What is this one?
Prior.
This is prior probability. And what is this one? This is likelihood, right? That basically talks about given x naught is transmitted, what is the probability of receiving y. So you can see a posteriori probability is product of prior times likelihood, and it's getting divided by some marginal probability. We can ignore that, and I'll just briefly tell you why. Because you have already mentioned that it will going to decide in favor of x naught when probability of x naught given y is greater than probability of x1 given y. If I replace this entire value here, it turns out to be p of x naught times likelihood divided by py is greater than p of x1 times probability of y given x1 divided by py. Now marginal probability we are not concerned about, because you can see this is going to cancel from both ends. So essentially we are going to decide in favor of okay. So you have raised your hand, you have some question, you can ask me now. You can unmute yourself and ask me. So you can see it's going to decide in favor of x naught when probability of x, this term prior times likelihood for x naught is greater than the prior times likelihood for x1. Now we are already given these two in the question, if you remember. It is 2 by 3 and it's 1 by 3. Now our concern is to compute this likelihood here, p of y given x1. Now let us just refresh what y is. Y is some x plus n, right? And this is already mentioned as white Gaussian noise. So it has some PDF or probability density function. And what is the x here? So x is a deterministic number. By the way, x is deterministic when we are talking about this p of y given x1. Given x1 means we know already x. That is the deterministic part. The only thing that is unknown is random part. When we are talking in context of probability of y given x, that is the scenario we are talking about. So n is Gaussian means it has a PDF that is given as this. You're already familiar with the structure, I am assuming. So this is the PDF of noise, white Gaussian noise. And the issue is we are talking about finding the likelihood, probability of y given x. So we need another slide here. So we need to find probability of y given x, where y is equal to x plus n. N PDF we already know, pn n, and x is some deterministic because we are conditioned on x. So basically means this is nothing but the PDF of shifted noise by mean x. So what do I mean by that? In y there are two parts, x and n. Now conditioned on x, so x is known to you. Known means deterministic. Only unknown part is n, that is random, and it has some PDF. So when I am asked to find the likelihood here, that is p of y given x here, that is, but y here is nothing but shifted noise which has a mean x, right? So this is the same as PDF of noise where y minus x given x. And we are going to make one assumption here, that is not an assumption, actually we know that message and noise are independent. So that means this x here and this n here are independent to each other, and that's quite obvious, because what message you are going to transmit from transmitter side has nothing to do really with, or there is no correlation to the noise that is getting added. So when x and y are independent, x and y are independent, we can write probability of y given x as probability of y only, right? Using that argument, this is probability of noise y minus x here. So this probability is going to be 1 over root over 2 pi sigma square e to the power y minus x square divided by 2 sigma square. Now when I put this value in the equation, so that is p of x naught, p of y given x naught greater than p of x1, p of y given x1. I can replace these values here in place of likelihood. But there is one thing I would like to point out here. This is for the Gaussian noise. This is for Gaussian noise. But the question that is given to us, is it Gaussian? This is not a Gaussian, right? And actually if I am to draw the PDF of the noise here, it will come out to be something of this sort. So from 0 to 2, at 0 it has a value of 1 over 2, so this point here is going to be 1 over 2, and then it continuously decreasing till it becomes 0. So this is the point 2 here, this is 0, and it's symmetric around the origin, goes till -2. So whatever I have told just now in terms of likelihood calculation, this here is applied for Gaussian noise, but the question given to us is not, noise is not Gaussian, noise at this triangular PDF thing. So in this case, what is going to be our scenario, like what is going to be P of y given x1, sorry, x naught. Can you tell me what is the PDF going to look like? We have seen that noise PDF is centered at 0. So what we just talked about, P of y x0 has the similar PDFs, that is of noise, is only going to shifted by x naught, right? So what is going to be the PDF in that case? The PDF shape will remain similar, but it's just mean is shifted. So which side of y-axis it's going to be, left or right? What do you think?
Right.
Are you sure? Because x naught is -1, right? It's
Oh,
it's 0. For 0 you are transmitting -1. So now noise PDF is shifted to -1. That means
left, left.
left, right. So we'll have something of this sort. Okay. Uh, we are only talking about likelihood, so that's okay. So now it's something like this. So this is the point. This is -1, and where it should end, this is -3, and in this side where it should be 1, right? So similarly, can you tell me about that PDF, sorry, likelihood for P of y given x1? I'll draw it with a different color. Which side it's going to be shifted?
So x1 is positive, so it will shift to right.
Okay, so now it is going to be something of this sort. It's at 1, -1 here, and 3 here. Fine. So this is all about likelihood. What next we need to do, because we are asked about the map receiver, so I need to product them with their priority probabilities, right? So if I now try to draw them on the same bar, so let us draw the likelihood, prior times likelihood corresponds to x naught here. So it was something like this: -1, -3, and 1. And this is what I am drawing is P of x naught times P of y given x naught. So what is the PDF of x1 is going to be? You think it's equal height or smaller or larger? As long as we are talking about likelihood, they are of same height. This was 1 over 2, this was 1 over 2, but this is only likelihood. Now I am talking about maximum a posteriori. That means likelihood need to be multiplied with the priors. So this prior here was 2 by 3, this prior here is 1 by 3. So what do you think the PDF of P of, just a moment, P of x1 times P of y given x1, the PDF is going to be taller than this or shorter or equal height?
No, it should change.
Yeah, so it should be taller or something shorter. So let us talk about this one 2 over 3, and this height was, likelihood was 1 over 2, so now it's 1 over 3, right, for this a posteriori PDF for x naught. And a posteriori PDF of x1 is going to be, this is 1/3 and height is 1, so it should be 1/6.
It should be shorter.
It should be shorter, so I should count somewhere here. 1 over 6. And when you talk about this map threshold, please ignore the figure where they are okay. When you talk about the map threshold, what is the point alpha you think going to be? So you told me that there are two probabilities and you are going to decide in favor of x naught when this is greater than this. So from that argument, what is your threshold alpha going to be, where it should be located?
One with the greater value.
um, One with the greater value, true, but when I talk about the figure where this alpha should be, like, how should I find the alpha? It's like, so in the
At the intersection of two PDFs.
at the intersection of two PDF, fine, so somewhere here. So I don't know really whether it's going to be on left or right side. I'm just drawing in context of intersection here. So basically when the value is going to be less than alpha, I'm going to decide on favor of x naught. Sorry, when the received signal is more than alpha, I'm going to decide in favor of x1, or otherwise it's x naught. So, and how do I find the intersection point here?
Equate both the expressions.
True, equate both these expressions. So I need to equate the falling side of x naught, falling edge of x naught, and rising edge of x1, right? So what was the falling edge equation for the noise? Let's check. Minus n by 4 plus 1 over 2, right? So minus n over 4 plus 1 over 2 was the falling edge expression, and rising edge was n over 4 plus 1 by 2, n over 4 plus 1 over 2. This is falling and this is rising. So when you talk about x naught, that is already being shifted by 1, so what it should be, minus n plus 1, that is minus of minus 1 divided by 4 plus 1 over 2, and there is a prior probability involved, and that is 2 over 3, right? 2 over 3. So this should be equated with 1 over 3 with the rising edge of x1, and rising edge formula is n over 4. Now it's shifted by 1, so that means n minus 1 by 4 plus 1 over 2. So let's see what we get here. 2 times minus n minus 1 plus 1, sorry, minus n plus 1 over 2 plus 1 is equal to n minus 1 by 4 plus 1 over 2. So on this side I have half, on this side I have 4, n minus 1 plus 2n plus 2. This is 2 here, is equal to 3n plus 1. N is 1/3. So the intersection point here, yes, obtained by equating as 1/3 is the option there. Yep, 1/3 is going to be my answer. But make sure your assignment might have some different prior probabilities. I mean, the calculation remains same, but your prior probabilities might very well be different. So based on that, your answer is also going to change. So you need to careful about that. The procedure still remains same, but based on the prior probability, the answer can very well change. For example, if I set this prior probability here 1 by 3 and this one here as 2 over 3, then this calculation will change here. Rising edge and falling edge equation will remain same, but the multiplicative factors are going to change, and based on that, definitely your, I mean, there is a good chance that your threshold is also going to change. So you have to careful about that. You can just blindly put this value in the answer. So we are done with this question. Let us move to the next part. So we are asked to find the new threshold value in the question if transmitter is transmitting using BPSK symbol such that 0 is mapped to 0 and 1 is mapped to 1, and with rest of the parameter remains same. So what do you think I need to make change in this question if I would like to draw the a posteriori PDFs here compared to this figure? What is going to change in this question number 10?
P of x naught.
P of x naught. So now there is any there is not any change, right, in P of x1. So let us P of I'm sorry P of y P of x1 given y, right? That is the a posteriori PDF. So let us draw that first because that remain unchanged. So that one have a height of, okay, 1 over 6 we have already seen, and is centered around 1, 1, 3, and minus 1, 1 over 6 height. So what happens to the other one, where it should be now? When 0 is mapped to 1 now instead of minus 1, where should be the a posteriori PDF?
It's around 0.
It's around 0. Okay, but is there any change in height, or the height remains same compared to the figure in this slide? Height remains same, right? Because there is no change, the parameters doesn't change, it's only the shift in the mean. Earlier there was a
Yeah.
shift of minus 1, now there is no shift, so it's going to be the here somewhere here. Okay, this one and this one, this is 1/3, this is minus 2, minus 2. So what should I do next? Okay, in terms of this equation here that we are equating earlier, what is the change going to be there?
That is shift minus n plus 1 will be different.
Okay, so let me just try to copy paste this
The
one.
intercept is not +1 here.
uh,
It
okay.
will be 1/3.
uh, Sorry, can you repeat yourself once?
Uh, Here the um, intercept is +1, right?
Yes.
Here in the second, in this question, the intercept is 1/3. Slope will remain same. Uh,
Okay, so let us the rising edge, falling edge remains same, right? Only the main thing changes. So what I am seeing, this +1 should not be here now, right? That is the only change, or is it there something else?
Yes, correct. Plus 1 is not there.
Because there is only change in the mean, because you have shifted it, but nothing else changes really. So only that +1 will not be here now. So it's 2/3 minus n over 4 plus 1 by 2 is equal to 1 over 3 n minus 1 by 4. Did I make any mistake writing, or okay, fine only. So this is 1 over 2. So now I have minus n over 2 plus 1, and here I have n minus 1 over 4 plus 1 over 2, n minus 1 by 4 plus minus 2n. So this 4 comes up here, it will become 2, and that is 3. So here, and we we have minus n. 1. Okay, I guess I did something wrong here. The question is where. So can you point out the mistake where I went wrong here? I guess this is +1 here. So this is 3n. Sorry about that. So it's 1, right? Just let me confirm once. 1/2 here, n minus 1 by 4 goes that side. Fine. 2n.
Yeah, got 1.
1 na? Okay.
Yes.
So the threshold, map threshold, is going to be 1 here. So I guess the options, none of these are correct. So let me highlight it here. Okay.
I am not understanding about the prior values used here.
Okay. So let us start from likelihood here. That's a good starting point. So we have discussed the concept of likelihood PDF here, right? uh, till now there is any issue like okay, we have the noise PDF, that is the PDF of n, right? Now when we talk about likelihood, it's the PDF of y given x naught. Now when I talk about given x naught, that means x naught is fixed, it's not random anymore. So y is nothing but a shifted version of n. Like n was some zero mean random variable, now y is some mean some same random variable with mean x. The PDF shape remains same, it's the mean only gets shifted. So till this point we have obtained the likelihood PDF as this. You have no issue with this, right?
Okay.
This p of y x naught, or I need to explain it? Like it's fine, like if you tell me that, I'll explain it better. Like I'm just trying to see that where we can really start, like
I'm
after. Hmm.
asking at the transmitter side only the probability of the X naught is taken, you are telling.
Yes, it's not exactly
That is prior probability.
yes.
So at the in the problem,
Yes.
when 0 is mapped to 0 and 1 is mapped to 1,
Hmm.
what is the prior probability?
The prior probability remains same only. That is, it's still p of, okay, you are confusing about this part, I guess, here, right?
Yeah.
Like p of x not given 1. Okay.
Yeah,
I
yeah,
got it.
that one, that one. Yeah.
Okay, okay, I got it. So there is one issue here, like in the question, actually it should not be x here, uh, like it can be x here, but here it needs to change to m. Like your message are zeros and ones, right? Your messages is this sequence. When it comes to
Yeah.
modulation stage only, then you are mapping 0 to -1 and 1 to 1. So when
Hmm.
I am writing x is minus 1 and 1, so here the probability of it should not be x is equal to 0, it should be m equal to 0. Now
I
in
got
the
confused with that.
okay, in the next question, that m to x, this transformation is m0 then x0. So this prior probability, there is no change. Prior probability of the message, and message is a one to one mapping with the symbol. There is no change in prior probability, but yeah, I got that point. It should be m here in both these cases. M is equal to 0 and m is equal to 1. I think this get rid of the confusion, right?
Yeah, okay.
Fine. Just a reminder here, none of the options are correct. Your correct option should come out to be 1 only here. So this is about a true false question. So the statement is made as follows, that the scrambling sequence doesn't influence the output of soft decoder. Okay, so before answering this, can one of you point out what is soft decoder? And if we are saying a soft decoder, there should be something called as hard decoder. So what is that really? Let us
In,
yeah.
I think actually I didn't cover those lectures, but as of my knowledge, hard decoder is the one where we will threshold the output to some values. But whereas in soft decoder, we will take the real values itself. Is it correct?
Okay, by real value, what do you mean? Like, uh,
Means at the out the receiver, whatever we'll receive, uh, that real values only we will consider for decoding. But in hard decoding, we will threshold it. Uh, like if it is above 0, give it +1, below 0, give it -1, like that we'll do.
yeah, like you are almost correct. At least in context of hard decoding, you are exactly. Like for example, hard decoding. If we okay, let's talk about the nearest distance detection. It
You
might
were
be
telling about that one hard decoding when it was covered.
yeah, in the demodulation stage. This all whatever we are talking about are valid in demodulation stage only. So let's say in QPSK constellation diagram is there, and 00 is being transmitted, and your let's say your received signal is somewhere here. So according to nearest detection rule, you are going to choose this, right? This is, let's say, 01. So hard hard decoding means that in the demodulation stage you already made the decision that 01 is transmitted, as she told correctly. So and the so it's like receiver is confident about his decision, that even if 00 is transmitted, just because the noise what is that uh, corrupts the transmitted symbol, so that your received symbol is here, and you apply the nearest distance detection rule, and you obtain your transmitted symbol to be 01. So receiver make the decision there onwards. So this 01, even if it's incorrectly decoded, this will go through the scrambler and then LDPC decoding, that will happen. When it comes to soft decoding, what they do, they don't make a fixed decision. Like they are not deterministic. They calculate the probabilities, that what is the possibility that the transmitted symbol could be 00 or 01, 11 or 10. So let's say hard decoding is more like in the demodulation stage, receiver decide it's 01 is transmitted, and that's it. That's a fixed. When it comes to soft decoding, it doesn't make that decision, it just calculate the probabilities and keep them as it is. So let's say for this case, the uh, the probability of transmitting 00, let's pick some arbitrary probability, is let's say 0.4, this one is 0.3, this point is this one is 0.6, let's say this is 0.2, this is 0.1, and this is 0.1, so they should add up to 1. So what the receiver do, even if this is the most probable, it doesn't make the decision that uh, 01 is transmitted. It calculates the probabilities, keep them as it is, and feed these probabilities, which is actually calculated as log likelihood ratio. We have seen in lecture most likely. So it is then going to feed into the LDPC decoder. That okay, you take these probabilities and make the decision. So basically, the decision is not made at the demodulation stage. So hard decoding is all about making a confident detection at the demodulation stage. So even if there is error, that error will propagate. And soft decoding is about calculating the probabilities and feeding those probabilities to the LDPC decoder. That okay, I have calculated the probabilities. You see now, these are the probabilities that this received symbol can be these symbols, and there you will have this likelihood. You take the log of that and take the ratio, and if it cross the certain threshold, you make the decision. But that's up to LDPC decoder, not at the remodulation stage. And it is seen that when you do the soft decoding compared to hard decoding, you observe a kind of let's say in dB terms a 3 dB gain, almost 3 dB gain. So 3 dB gain, uh, you know that it corresponds to a multiplicity factor of 2. So that means user can be at a distance of uh, twice the distance in case of soft decoding compared to hard decoding, and still obtain the same SNR. So let's say in context of hard decoding, if the receiver is observing some SNR at 100-meter distance from the base station, now if you employ soft decoding, it is going to observe the same SNR at 200-meter distance. It's even if it looks small, it's a huge benefit actually, that you are able to maintain the same level of SNR even if your distance is twice. So that is what soft decoding is. So soft decoding is not making a decision on its own, computing the ratios, the probabilities, and feeding those to the LDPC decoder. So
Sir, I have a question.
yes,
Sir, how can we say that soft decision decoding have 3 dB gain? Like, is there any mathematical form or what?
okay.
Is it based on experiments?
Uh, to be honest, I don't exactly know the reason behind it, but as per my understanding, it has been verified experimentally that instead of doing hard decoding, if you do soft decoding, you are going to observe this 3D gain. Yes, like this value is experimental, of course,
Okay, sir.
but the reasoning behind it, I don't really know. But that's a good point, like that's a good thing to look at if you want to dig deep into this.
Okay, sir.
So this question then, the scrambling sequence, is that going to influence the output of your soft decoder?
No,
Okay, but
because it is taking probabilities.
you are taking some probabilities, right? Okay, but let's say your scrambling sequence, let's talk about one particular bit, let's say it's 1, right? Your scrambling sequence, a particular bit I'm talking about in the pseudo random sequence, that is going to be XORed with a data bit. And if your scrambling sequence, that particular bit is 1, what is going to happen? It is going to flip your data bit, right? If you are XORing with 1, if your input bit is 0, it will
Yes,
become 1. If it's 1, it will become 0.
1 0.
Yes.
And when you do that, your probabilities change, right? Because your bit itself has changed.
Yes.
So your scrambling sequence is indeed going to influence your soft decoder output, right? Because soft decoder takes into account the probability of zeros and ones, log likelihood ratios, and the scrambling sequence has the capability to influence that. If it's been 1, that means your data bit basically flipped, so that probabilities change there. So it is going to impact the output of soft decoder. I'm not saying in a bad way or something, but it is not the same thing without scrambling, right? Like in absence of scrambling sequence, maybe something that is feed as 1, now it's going to feed as 0, so that probability changes now, so it's going to influence the soft decoder output. I hope this is
But
clear.
if
Yeah.
I have one question.
Yes.
You told that 0 1 will be flipped to 1 0.
Yes.
But soft decoder is considering the probability of 0 1 only, no?
Let's say at the demodulation stage, you have this bit 1, so I'm talking about bpsk only. So you have some probabilities of that being 0 and 1, right? Some fixed probabilities for that particular bit. Let's say it's the transmitted bit was 1, and when I do soft decoding, basically I calculate the probability of that being 1, probability of, let's say, y being 1 we computed as 0.7, and probability of y being 0 we compute as 0.3. Now unfortunately this bit, whatever it is being if the scrambler bit is, it is XOR with 1, basically that particular bit y here, that is going to be y complement. So now the bit itself that is going into LDPC decoder is changed, right? Like what I am saying, if the uh, scrambling is not there, y is going to feed to LDPC decoder. But now since there are this XORing with scrambling sequence, y complement is going there, so your output is not going to be the same, right?
But you told the decoding is done on the probability basis that we get from the transmitter side. So, where 0 1 is transmitted, it is taking the probability of that one.
Okay, you are saying let's say you're talking about can you just repeat it once, like let's say if
You told
transmitted.
0 1. You told while explaining this, it will take soft decoding is done on the probabilities. Like 0 1 is transmitted and it is taking how much probability that it is getting received, I think.
Yes, in soft
Huh?
uh, sorry, can you just
So when it is taking the that thing, how you are telling that the change in bits will not interfere with decoding itself?
no, no, like it is going to be rightfully so I think we are confusing between the LDPC decoding and the decoding, what I mean at remodulation. So these two things I think we are kind of getting confused about.
Yeah,
So
yeah,
if
correct.
we see in the perspective of let's say scrambler here, if there had not been a scrambler, y is going to be fed into LDPC decoder, right? But now
Yes, correct.
scrambler
Mm.
is there,
Oh,
and
because
if that turns out to be 1, now y complement is being fed. Like if it's been 0, now 1 is fed, now it's 1, it's 0 is fed. So from that point of view, it's going to influence the output of soft decoder.
Okay.
It's not going to cause any error or something like that, or in a I'm not saying it's going to impact in a bad way. I'm just seeing things from the scrambler point of view, that if the scrambler is not there, you would have been feed Y to the LDPC decoder, you get some output. But now since the XORing with scrambling sequence is there, you are now feeding Y complement, so the LTPC decoder output is going to be different. So the scrambling sequence in that sense is going to influence the output of your soft decoder thing. Okay, so about this question here, there are 110 PRBs is allocated across 10 OFDM symbol. So we are supposed to calculate the total number of resource element available for the user to transmit the physical downlink shared channel. So what should be the answer for this? Like, how can I calculate the total number of RDs here? So when I talk about 1 PRB across 10 symbol, one PRB across 10 symbol, how many resource element I have here? So there are 12 subcarriers and I have 10 symbols, so I need to multiply with that, and I also need to account for the subcarriers reserved for pilot transmission, right? That is 6. So it comes out to be 114. So total R is 110 PRB times mean of 156 and 114. So it's 110 into 114 only. This many RDs are available to transmit that PDSCH. Now in the earlier question we have not given the code rate or the modulation scheme. Now we are given those also. So how should I find the number of informations bits that I can transmit based on that earlier calculation? Anyone would like to volunteer? How should I proceed? I have number of resource elements available. We have already obtained 114 times 110. What I need to do on top of that to get the number of information bits? So number of REs that multiplied with
Code rate, is it code rate?
the modulation order, right? So what is the modulation order for this particular question?
$256 8.
That is 8. Okay, and I have to multiply something else on top of that.
code rate.
And what is the reason behind multiplying the code rate? Like basically I'm asking why should I do that?
We should get the information bits now. That's why.
Okay, so you are saying as the code rate is given as 700 divided by 1000, so out of every 1000 bits basically 700 is my useful one and rest are parity
Information.
bits. Okay, so they don't carry any information, so that's why I need to account for them. Okay, so that is 114 times 110 times 8 times 700 divided by 1000, and the answer is supposed to be in terms of an info by 100, so it should be 114 times 1110 into 8 into 10 here. uh, okay.
Divide by 10, right?
uh, should yep. uh, Thanks for pointing this out. Sorry about the mistake. So okay, I think it's not divide by 10, right? It's much lesser than that.
Yeah.
It's basically 10 to the power
It's
5
divide
here.
by 10 power 5. Yeah.
Okay, okay, thanks. It should be 10 to the power 5 here. So the same question, now it's told that user is allocated 13 symbols. If you remember in the earlier question it was 10 symbol. So what is the gain we obtain in terms of RE? So how should I calculate that? The modulation order and the code rate remain unchanged, so you can ignore them. We can work based on the PRBs only. But how do I proceed? Number of PRBs also doesn't change, so number of PRBs, modulation order and code rate we can ignore. We can work on one PRBs across the symbols. So what is the number of symbols in earlier case? It was across 10 symbols,
10.
right? So what was the number we obtained? Number of REs in a PRB?
114.
114. So can I do this thing like to further simplify, since earlier it was 10 symbols, now I have 13 symbols, so increment is kind of 3 only, and that is on top of 10, so this should give me the percentage gain, right?
Yes, correct. That is simple.
So it should be something like 30%. But is that the correct way or I'm doing something wrong here?
I think number of symbols is different. The number of REs. It is 114 into something was there.
Number of REs.
100. for 10 symbols.
Mm-hmm.
You have written it as 114.
So what it should be?
114 into 100 or something like previous problem. You had multiplied with 100.
Okay, that is the number of PRBs, so that doesn't really change. That was 110 PRBs, that remains same here also, there also. So they are going to cancel out, right? So they are not having much impact here. So we can still work on one PRB across symbols because that is where the change happened. The number of PRBs remains same in the both cases, so we don't really care about
Then
that.
what you have calculated, should be correct.
Okay, but are you sure about that? Like, what happens when we have, as this question, one PRB across 13 symbols? How many REs do we have now? Symbols mean in time duration, that is 13. Multiplication with, what should I multiply with? 1 PRB mean how many subcarriers?
12.
12. And is that all, or I need to do some subtraction or something? 6 is reserved, right, for wireless transmission,
Toilet.
so it should be minus 6, so that would come out to be 150. So earlier I have 114, now I have 150. Let's see that. So it's 36 over 114 times 100. So answer, if you will do, it will come out to be something like 29.82%. So why did it differ from the answer here? Here it's exactly 30, it's 29.82. Which one is correct and why?
We had not included the pilot.
You have not included the pilot. In which one?
Second one.
Second
Second
one.
one we have subtracted, but in the first one it was there.
So here we have not included the effect of pilot, right? Did
Correct.
not consider the reserved pilots. So which one is
Sir,
yep,
the answer is coming 31.57 like that. 36 by 114 multiplied.
okay. Uh, just let me check once. Yep, it's 31.57. True. It should not be. I made the mistake here. Thanks for pointing it out. It should be 31.57, right?
Yeah.
Thanks for this. This is 31.57. So which one should I consider correct? Like this 30% or 31.57?
31.57.
Yeah. So sometimes question can trick you in that way. So even if you can see the change in number of symbols, so you might be prone to do that based on the number of symbols only, because rest of the things remain unchanged. But the issue is when I go for only symbols, it doesn't account for the pilot reserved in one slot, and that will get you into trouble. This answer is incorrect. So this question, can you please answer for me, that in the receiver, while we use passband filter while trying to recover the baseband signal, basically what is our goal? To suppress the effect of carrier frequency offset, to limit the passband noise, to increase the gain of system, or to suppress the effect of carrier phase offset inside passband? Which one you think should be the answer?
Is it option A?
Option A says the suppress the effect of carrier frequency offset across pass band. But is that the goal
Second
of
one is correct. Actually.
second one, to
To
limit the
limit the passband noise, it will do that one, passband filter.
okay.
R3 is also likely to be correct to increase the gain of the system in the required band.
Increase the gain of the system in the required band, but that's the task of the amplifier, right? Actually,
Yeah,
if your
correct.
received signal is there, RT, so you are, this is this expression, root 2 I cos omega naught t minus root 2 q sin omega naught t. You multiply it with the output of a local oscillator, right? Local oscillator, it basically generates a wave cos omega naught t. You feed RT on to that, it's getting multiplied, and then you use a phase shifter basically to produce sin omega naught t and feed it, and then comes your passband filter, right? Passband filter here, passband filter. So are you still sure that with your answers that passband filter does that? This is the RF signal you have received. This is the down conversion you are performing in the local oscillator, basically multiplying with the carrier of same frequency. So are you sure with your answers, like to limit the passband noise or to suppress the carrier frequency offset? What does really the primary goal of passband filter here?
So phase shift,
Uh,
carrier phase offset.
Like
yeah.
after multiplying, we will get the higher frequency components.
Hmm.
Um, so it will filter out that higher frequency component.
So what it will be left with? There will be mixture of those things. I mean, there will be higher frequency component, there will be lower frequency component, like there will be 2 omega naught, and there will be omega naughts also,
Yeah,
and
it,
there will
it
be,
will just pass the higher frequency components.
but what I will do with the higher frequency components, because the
Okay,
all
okay, sorry, not it is not high pass filter, it is band pass. Um,
passband filter is actually not a band pass filter. So
okay,
can you, okay, let's try to see it in a different way. Your RT, that is root 2 I cos omega naught t and all that, is this a passband signal or baseband signal?
Baseband.
And what do you mean by baseband?
The original message signal.
Base, okay, quite correct, but basically baseband means when it's centered around zero frequency.
zero frequency. Yeah.
Okay, but here RT, here I don't see it centered around zero frequency, right? RT is the received signal, and this is the passband signal actually. That is a high frequency. You are multiplying. So what is the our goal with multiplication with cos omega naught t and sin omega naught t? What is we are doing, trying to do here? RT is something you have
Like
received. Yeah.
if we multiply it with the same frequency, sorry, same sinusoids, we will be getting one DC signal, like which doesn't have any frequency component, and means which doesn't have any sinusoid and higher frequency component. So if we remove that higher frequency component, we'll get our baseband.
So basically you are saying we are doing passband to baseband conversion here, right?
Huh.
Okay, so effectively if I just try the multiplication here, cos omega naught t multiplied with this signal, so this will become cos square omega naught t, so this would lead to something 1 minus cos 2 omega naught t, or sorry, cos 2 omega naught t minus 1. So essentially you are saying I am supposed to get something like I here and q here, right? So those have no high frequency components,
Yeah.
and then I'll just add them up. So I'll get here I plus jq, that is my complex baseband signal, right? So now you tell me what is the answer for passband filter, what is it exactly doing? It is basically recovering the in phase and quadrature components, right? So actually none of these options are correct. None of the options are correct.
Sir, you said passband filter is not same as baseband band pass filter. Can you say what is the difference?
Okay, so I guess we can clear that in the next stage, like in the next question. But passband filter basically here what you see, like what kind of filter I can call it? Can you find similarity to something here? Like it's calling passband filter. So is that band pass, high pass, low pass? Anything you find similarity?
It is similar to low pass, I
It
think.
is similar to low pass filter, right?
Yeah.
So let us move to next question. There I will answer that. Okay, I think I make a big mistake here. Can you point out that mistake? Sorry about confusing you all again and again, and this is truly a mistake I made. So can you point it out here? What mistake I made?
It limits the passband noise.
Yeah, true. Actually, I make the changes in some other slide, and I didn't pay attention to what is done here. Sorry about that. So whatever I discussed here is applied to a low pass filter. So this should not be a passband one, first of all. This is in context of low pass filter. So it turns out I get confused myself. And can you please point out why it's necessary to implement this passband filter here? like why you should use a passband filter? What is the goal of that?
Noise in the passband will be filtered out.
So you are saying that earlier you are receiving signal that is at some certain let's say uh, this is my signal part, so that is limited between these frequencies minus f naught minus f1 to f2 here minus uh, sorry f2 to f1 here. So what is the requirement to limit the passband noise, because my signal is already in that passband only, right, centered around some carrier frequency f naught. So why we need to filter out the noise at that particular passband? Are not the noise is also supposed to be in that band only?
Sir, didn't get what you are asking.
Okay, I'm asking like if you received signal, let's say you received RF signal is something like y is equal to x plus n, right? So your x is
Yeah.
this x has this kind of spectrum and the signal is limited in these bands. So what is the necessity to pass this signal through a passband filter? Like the noise is already in that band only, right? Or is it not? Like why do I need a passband filter at the first place? It's like x is already limited to that band only, so why should I need to pass y through the passband filter? So when you talk about noise, it's additive, white, Gaussian, right? So there is a term white in it. So what does this white signify here?
Mhm. Power spectral density is constant.
Power spectral density is constant and that is across all frequency, right?
Yeah.
So it's like a constant line if I look at its frequency domain representation. So if I don't employ the passband filter here, the noise throughout the entire frequency range, that is the capability of your receiver, is going to interrupt this one also, right? So essentially I need not these things at all. So when I pass through passband filter, it basically filter out this entire part. There is no signal here, so there is no information loss for me, but the noise is getting filtered out for this entire part. So what I have, the signal is already in this passband. Now the noise we are also considering, that is also limited to this passband. And this question here I guess you have already answered to that in context of the previous drawing. So what is going to be the answer here? The use of low pass filter. In the baseband processing, why should we employ the low pass filter here?
Option B.
Option B, to the transmitted IQ samples. So by the way, I'm extremely sorry for that mistake. I was not paying attention. So what you guys told are absolutely true. For like low pass filter is to obtain transmit IQ samples and the passband filter is to limit the passband noise. It's just I thought I have changed the question but I haven't and I didn't pay attention, so I made this major mistake. Please ignore that part. So about this question here, the received RF signal is like this. Now I have a phase offset in the local oscillator, and my received signal comes out to be like this, R hat T. So how I'm how I'm supposed to find the phase offset? So how how should I proceed to find that? Like, what things I need to do here? I have RT here, that is square root of 2 IT cos omega naught t minus root 2 q t sin omega naught t, fine, plus some noise. So what is the next step I should do? Local oscillator is generating this, so I'm going to multiply this thing with RT here. So that is square root of 2 IT cos omega naught t plus phi times RT. Sorry, there is no IT here, this part will not be there. Just square root of cos omega naught t plus this. So this will come out to be 2 times IT cos omega naught t and cos omega naught t plus phi minus 2 qt sin omega naught t cos omega naught t plus phi plus nt times again square root of cos omega naught t plus phi. So this entire thing should go through low pass filter, and what we are going to obtain here, when I pass this through the low pass filter, IT cos phi, right? 2 cos a plus b is cos a plus b minus cos a minus b over 2. So yep, IT cos phi, what I am getting here. What is the second thing I should do here? Multiplying root over cos omega naught t plus phi minus pi by 2 times RT, that is minus square root of 2 sin omega naught t plus phi times RT. And what is this going to produce? Okay, this is not going to produce this one here. I forgot to include this term. So sin a cos b, 2 sin a cos b. So what is the formula here? 2 sin a cos b. Let me that confirm that once. Can one of you please tell what is that going to be?
Um, Sine of a plus b, uh,
Sin of a plus b.
a plus b by 2 plus cos of plus sine of a minus b by 2.
Sin of a minus b. Okay, so from this calculation what I am supposed to get here?
Divide by 2 will not come, sir.
Okay, divide by 2 will be
Sine
gone.
of a plus b plus sine of a minus b.
So it
Mm.
is going to be qt sine of minus phi, right? Minus q uh, sine of minus phi, that is it cos phi plus q sin phi. Similarly, what we are getting from here, I keep the minus outside, 2 it sin omega naught t plus phi cos omega naught t minus 2 q t sin omega naught t plus phi sin omega naught t plus noise times sin omega naught t plus phi. Passing the entire thing through LPF, what we are getting here is, from this one I am getting 2 it sin phi, and from this is 2 sin a sin b,
Sine sine 4 omega naught t plus 5 minus sine 5.
so that is sin a plus b plus sin a minus b.
Yeah.
So let us write in terms of a and b's.
So it will sine 5 plus sine 4 omega naught t plus 5.
Okay, so here should be 2 qt sin phi. That's what we are going to obtain, right? Or I am doing something wrong here. Sin a sin b is that sine a plus b or it should be cos?
Sir, that first term will be sine a plus b plus sine a minus b. That second term will be cos a plus b, yeah, minus cos a minus b.
Okay, so you are saying this one should be cos, right? Both of them, and there should be a subtraction here.
Yeah, for 2 it sine omega naught t plus phi into cos omega naught t, that will be equal to I of t into sine phi plus I of t into sine 2 omega naught t plus 5.
Okay, you are talking about the first term here in the first slide here.
Yeah, in the first term, two terms will come. Alright.
Yes, two terms will come, but will only contain the terms without omega naught uh, phi, right? So which one is that? It should be cos.
Yeah, cos.
So this one here should be cos, right? But I have just can you please tell me like for 2 sine a cos b, what is the formula again? Sine of a plus b plus sine of a minus b.
Plus sine of a minus b.
Okay, okay. So using that argument, it still comes out to be sine here only, right? Because it will be like sine of 2 omega naught t plus phi and minus sine of phi. I mean plus sine of minus phi. So essentially minus sine of phi. And here there are two sine a sine b. So is that cos of a plus b minus cos of a minus b, or is it something else?
It will be 2 sine a, sine b will be, mm, yeah, cos of a plus b, sorry, cos of a minus b, uh, minus cos of a plus b.
Okay, so it should be cos of a minus b and should be a plus b. Thanks. So again, this is going to be cos phi here. This is going to be cos phi, and the minus sign will remain. Okay, so it minus 2 it sin phi plus 2 qt cos phi. And this entire thing should be multiplied with this j while combining. So essentially if I ignore the q multiplicative terms 2, it will be it cos phi minus minus it j sin phi plus q sin um, phi here plus jq cos phi. Okay, now if I try to rearrange these terms, I plus jq times cos phi here minus or it should be plus here I plus jq phi, right? Okay, it's minus only j sin phi. Did I write minus j square plus? Okay, okay, it looks fine. So it's essentially I plus jq. I can write it cos of minus phi because inside cos of minus x is cos x, and here it will become I plus j phi. I can take the minus inside, sin minus phi j. So this I plus jq is your complex baseband signal, that is S here. So this is S times cos of minus phi plus j sin of minus phi. So essentially S e to the power minus j phi plus some noise term will remain, we are ignoring that. So if I compare this expression with here, so root over 3 by 2, that means
Mm,
yeah, you are saying something.
60 degrees, it's 60.
So that minus phi is equal to 60 minus 60, so yep, phi is 60 degree, correct. So the fourth one is the correct one, but sometimes they can change the phi here, so accordingly that sign will be changed. You need to careful about that.
Okay, sir.
So thanks for pointing out all these errors I have been making, and thanks for correcting those also. So I think we can conclude this session now. Of course, if you have some questions, you can take that, or otherwise I'll conclude this session.
Yeah, sir, just can you tell the difference between pass band and band pass?
Okay, okay, yeah. Well, if it's pass band and band pass, uh, they are same indeed. They are same. Like band pass, we use more in the context of where we are interested in letting certain band of frequencies pass, and pass band is essentially the same only, same. Like in context of wireless, you will see more the pass band term because when you move your baseband signal that is centered around zero frequency to some high frequency content, so that create a certain band, that's why what we call pass band. So essentially they are same only, pass band and band pass. So what statement I made earlier that they are different, it's wrong actually. They are same.
Okay, sir. Thank you.
Okay. Okay. So thanks you all for being with me with the session. And if we don't have any question, then we can conclude and we'll meet on next Saturday. Bye.